welcome back to Efficient Algorithms, COMP526. In Unit 5, we'll talk about data compression and various nice techniques that relate to what we talked about in string matching and will lead to more advanced text indexing later on. The goal for this unit is that you know basic stuff about how to represent text in a computer, like the necessity for character encodings and what is standard to use there. Then on the other end of the spectrum, there's some clear impossibility results, and you should just be aware of them so that you're not fooled into believing strange claims, say. And then we'll look at a few concrete, well-known and widely used compression algorithms or encodings listed here, and you'll see them while we go. The last bit is maybe the most interesting for assessments as well. I'd like you to be able to take some of those existing techniques and slightly tweak and modify them, or at least apply them when they are useful. So as always, like in the past units, the goal is not just to understand how these methods work, but also what their properties are. Your goal in graduate level jobs won't be usually to implement an existing algorithm that's already invented and has been out there for decades. There is an implementation in most libraries. What you are for is for understanding what's inside the black box so that you can use it effectively and competently where it's useful and know its limitations. So nothing new on that front. That's the overview. It's mostly subsections for the different types of compression methods. We'll get to that. Before we do, though, I want to again set the scene and give some notation that comes up in the remainder of the unit, and also give a little bit of context and motivation for this whole thing. In Unit 4, where we just came from, string matching, we looked at how to work with strings, and we will come back to that in Unit 8 when we talk about text indexing. So there's various tasks you can look at what to do with strings. For now, we've looked at how to find exact matches of a pattern, but there's related things you can also do. Our assumption was always that we're given the string as an array of characters. So we can basically jump around with random access. So random access, again, meaning I can jump to the 17th index in one step. I can use indirect addressing for that. In this unit and the next one, the focus will be slightly different. We'll instead look at how to store or transmit strings. So not necessarily compute on them, but pass them around. So for a computer, that means everything is eventually binary. That will usually be our point to stop as well. In this unit, we'll look at how to save space. So reduce redundancy in data. In the second unit on this part, Unit 6, we'll look at how to transmit over noisy channels. So a little bit of error correction in there. Now, I also want to mention that a modern trend is to try to combine the two things, something I'm researching in as well. How can you store things in a compressed form, but at the same time compute on that representation without decompressing first? So the traditional paradigm is this split. You either worry about how to compute with your data, or you worry about transmitting it or storing it to disk. And the algorithms are separate. And the kind of new paradigm or upcoming paradigm that becomes more relevant is to compute directly on the compressed representation. But we'll at most touch on that briefly. I asked you up front what compression methods you know. And there's a big collection. So there's different classifications that I'll come to in a second. Lots of archive programs that you can use to compress files in a file format. And then also specific algorithms, some of which you've seen in the outline. So we'll come back to some of those. Yeah, arithmetic coding is a lovely one. Always wanted to put it in this unit, but it was too full already. So there's some knowledge in the room, but we'll start from basics for this part. So first discuss some terms. We have two types of texts when we talk about compression algorithms. We have a source text, which is what we start with, and we call that S, capital S all the time. It comes from a certain alphabet, the source alphabet, if we have to specify it, and it can be of arbitrary length. And then we have the coded text, which is the output of our compression algorithms. We'll denote that by capital C, and it can come from a different alphabet. Often the coded alphabet will be binary, but that's not always the case, because sometimes we'll do a chain of algorithms one after the other. And so the coded alphabet for one method could be the source alphabet for a second method. And so maybe only the last step is to go all the way down to binary. And we'll have two steps. When I say compress, we usually think about just this, taking the source text to go to the coded text. But it's only half the story. The life is only really interesting if you can go back from the coded text as well to the source text. So there's the two inputs, and there's two algorithms, and the order of the role of input and output is swapped in the two cases. There's two very broad categories of compression algorithms. They can be lossy or they can be lossless. In lossy compression, the decoding, if you go from the source text to your coded text and then back via decoding, you only get some approximately equal source text. It's not exactly the same. And you have to specify with some domain knowledge what is good enough. So they should be similar. But what that means formally depends on what you're doing. So usually lossy compression is done for some multimedia formats, or well, just media formats. So images, videos, sound, all that, where even the source text in binary was just an approximation of some real world thing. So if you take a picture with your camera, it's not the same as what you were seeing at the time. It's just some representation. So it's acceptable to modify that representation if it still looks the same to humans. So in this case, similar would mean a human being cannot easily distinguish the two. Then that's close enough, even though if you compare them bit by bit, they might be very different. Now in this unit, in this module, we'll not look at lossy compression. So that's kind of a separate topic because it needs much more domain knowledge. It has to be specific to a specific application. It's not to say that it's not interesting. So what's behind all these is another cool topic, but not for this module. Instead, lossless compression reproduces the source text bit by bit in exactly the same way. So if we restrict ourselves to lossless compression, then the question can still be, what is a good encoding scheme or a good compression algorithm? I'll use these two terms synonymously. So a compression algorithm, I always mean that there's also a decompression or decompression algorithm, decoding algorithm. So encoding scheme makes it a bit more explicit when we think about encoding and decoding. But the two terms mean the same for me. There's, again, depending on the application, different goals we can have. We will mostly focus on the size of the encoding in this case. For this unit, at least, that's all we care about. And we have a specific way to measure this. And that's, it can be expressed in terms of the compression ratio. And so we should briefly discuss what is the size of a string. Now, the length of the string as the number of characters is definitely part of the equation. So if I have some string, element, and here I'm using the notation sigma to the n. Remember, that's a string of n characters from this alphabet sigma. We could just say that's the length of the string. But if we ignore how many symbols in the alphabet there are, you can cheat. You can define the coded alphabet to be sigma to the n, just all n tuples of characters. And then your coded text could just be s with as a single character. And so it would have size 1. You compressed it down to 1. If that feels like cheating, that's because it is cheating. You can't ignore how big the alphabet is. If you think about writing this down in binary, you have to somehow encode each character. We'll come back to that in a second in much more detail. But to just cut that discussion short, we'll multiply the length of the string by log of the size of the alphabet as an approximation for how many bits you need per character. Now, for the experts knowing arithmetic coding actually achieves this to a good degree. We'll see methods that come close to this, but not quite. For the computation of the compression ratio, we ignore this. That's just a rough number. So we just take the length of the strings times log of the size of this alphabet. And then we take the ratio of those two things, the coded alphabet, the coded string, and the source text. Often when the coded alphabet is 0, 1, then of course log of 2 is 1, and so this simplifies to what's here. And the way to interpret the compression ratio is if it's below 1, then that's good, then we made the overall information less. We found some way to compress. But it could also be that it doesn't compress or that it even expands. So sometimes you try to compress and the output becomes bigger. So little fun question on this. Has anyone tried what happens if you zip a zip file? Maybe do it. It's a fun experiment. Think about what should happen. And then you can explore it. I think it's a good little motivational exercise. There's another question I asked you earlier before we even started with all of this. So very likely you won't have to answer this again. I want to briefly connect compression to some theoretical computer science topics that I think here very well motivate why you want to study those in a computer science undergrad degree. And for the conversion masters, why you should at least have a little glimpse of what they are. And the connection is as follows. If we think about compression as a general way to reduce redundancy or information, you easily come into the realm of these questions. So here's an image. I suppose many of you will know what that image shows. It's a fairly well-known one. The question is that compressible? Now, of course, you all know about JPEG and other more modern compression methods for images. Okay, JPEG is not what I want because it's lossy, but there is lossless compression methods. Like PNG has a kind of compression method built in for images. And there's, again, more advanced modern web formats for image compression. I know all that, but is that the best we can do? Can we compress that image further? On one side, it's an intricate shape with lots of little detail, which often means it's hard to compress. So if you use PNG for this, it doesn't compress it very much. Maybe the parts out here where it's almost the same color, it will compress, but these intricate details here, no. On the other hand, you know where this comes from. It's a fractal. It's called the Mandelbrot set. So there's a formula to compute that image. And it's a very short program, actually. So, I mean, look it up on Wikipedia if you've never read about this. You can find lovely visualizations online and so on. That's it's a lovely math topic that has nothing to do with the actual content here. All I'm getting at is there's a very short program that produces exactly that image. Why don't we take that short program as its compressed representation? The program is much shorter than a PNG representation if I take the high resolution version of this image. So it's much better compression. And this is what people observed, or what people studied. And it's been given the name Kolmogorov complexity, or descriptional complexity. If you're given a text, a source text S, the Kolmogorov complexity is the length of the shortest program that produces that output. So think of a little Python program with lots of little print statements in there, and you want to find the shortest Python program that produces a given text. Now, it could just be print, here's the text. That always works, and it's roughly as long as the text you started with. But sometimes, as in the case of this image, you can compress it much better by exploiting where the image comes from. You can write Python code that computes the fractal from its formula, and then it's a much shorter code than representing the image explicitly. That's kind of cool, because that's, in a way, the definitive answer to compression. Any kind of decoding algorithm has to be an algorithm that produces the text again. So if I take the shortest such program, that's the ultimate compression. So why do we have a list of different compression methods if there's a single answer for the best possible compression? Well, the unfortunate answer is that Kolmogorov complexity is undecidable or uncomputable. You can rigorously prove that there's no algorithm that always tells you the shortest program. And so I mean, the pessimistic point of view would be it's utterly useless. It's an ultimate measure of complexity that you cannot use at all because there's no way to find or compute that measure. So the positive take on it is, well, okay, we have to find methods that work well for the type of data we care about. Maybe this is only a worst case statement. There's no algorithm that always works to find a good compressed form, but that doesn't say we can't find methods that work well in many cases. Before we come to that, let me point out something slightly related. I just want to mention this as a little bit of motivation. Does anyone know about the Hutter Prize? Okay. Does anyone know about AIXI, A-I-X-I? Is an artificial intelligence theory where this person, Hutter, is involved. So compression, as we've seen, this Kolmogorov complexity idea, it seems to be getting at some fundamental question of, is there a structure in a given text? And that, in a way, is also what artificial intelligence has to do about its environment. If it somehow shall be able to predict and act according to its inputs, it somehow has to extract the structure of the environment, say, learn the laws of physics in some sense. That's a form of compression. And there's a widely ranging statement that essentially says, if you solve the problem of optimally compressing your environment, then you've actually solved the problem of constructing the best possible general artificial intelligence. If you want to read more about the formal version of that, you can do in Hutter's book. The prize is motivated by that, where he says, okay, let's try to operationalize that a bit. If you take a 1 GB of Wikipedia, just the text of some articles, and you can compress this to something much smaller than before, then you must have learned something about what makes Wikipedia articles, what makes human text, what makes human knowledge, maybe even more. And so he set up this competition, and you see it's very active. Just this summer, someone improved it by another little bit and earned $5,000 for it. So just as a little note aside, compression can sometimes be just the dry act of compressing your zipping your submission before you upload it to Canvas, as you will do for your assessments, right? But it is actually a very deep theoretical topic with lots of implications. All right. But coming back to the module, here will be a little less ambitious. If we can't always compress in the ultimate sense, we can instead ask, well, what can we do? And lossless compression methods that exist usually come in, they kind of fall into one of those two categories most of the time. They either exploit that some characters occur more often than others, or they exploit that there's repetition in text in the sense of certain things occurred almost literally like that before. And those are the two key parts that we'll exploit. I also want to point out at this stage another negative result that you'll cover in the tutorials in more detail. You cannot always compress. If you want an algorithm that works all the time, it has to make some things bigger. And that's also why I asked you to zip a zip file and see what happens. I mean, I can spoil it and say it gets bigger ever so slightly. And you can zip the zip file, the zipped zip file again, and it gets ever slightly bigger again, and so on. Maybe at some point it stabilizes. But that's one kind of example that illustrates this. There's no free lunch in this case.